Hello viewers, welcome to my channel. This is Rekha Venkateshwarlu, Assistant Professor of Physics, Government Degree College for Women, Nalgonda. In the present class, now I am going to discuss the topic Gauss law applications in the case of volume charge distribution. This is Basic Physics 5th semester Electromagnetism first unit syllabus. Okay, so the contents of the lecture, the contents of the present lecture are introduction, then volume charge distribution, uniformly charged conducting sphere. After that, we will discuss Gauss law application to volume charge distribution in the case of uniformly charged non-conducting sphere. Lastly, we will see the conclusions. Okay, now wait. Yes, we look here. So let us consider a uniformly charged conducting sphere. Here R is the radius of the sphere. The charge Q is distributed over this conducting sphere. Right, O is the center of the sphere. Now, by using the Gauss law, we have to calculate the electric field strength at external point on the surface and internal point. So let us see one by one how we are using the Gauss law in calculating the electric field strength simply by using the symmetry of charge distribution. Right. So here P is a point which is external point at the distance small r from the center of the sphere. So now you assume that a spherical Gaussian surface passing through that point. So this is a spherical Gaussian surface. On this surface, again you consider a small area element ds. So the direction of ds bar will be perpendicular to this area element, thus will be in this direction. But the electric field strength at this point is radially outwards, like this, radially outwards. E bar direction also perpendicular to the surface at that point in this direction. So it is very clear that at this point, ds bar and E bar are both are in the same direction. So what is the angle between ds bar and E bar here? That is 0. Then the flux through this area element given by d phi equal to E bar dot ds bar. Okay. So the flux through that element that is E bar dot, we can write E bar dot ds bar. This is the flux through this small area element. But we have to consider the total flux coming out through this entire spherical surface. So for that we should integrate this E bar dot ds bar. So integral of surface integral of E bar dot ds bar gives the total flux coming out through this entire spherical surface. Right? So here, so what I am saying is, so we are considering an Gaussian imaginary spherical surface. So the point P lies on this surface, right? So at this point, wait. So at this point, so again we are considering the small area element ds bar. Then the direction of the small area element is in this direction. Okay. Then, but the direction of electric field strength, the direction of electric field strength is radially outwards. It is also in the same direction. You take any point. You take at any point. Here is a small area element. So I will show that. So this is a small area element. Here I am taking again small area element. Here also I am taking the small area element. Here also small area element. So this is here it is a ds. Okay. This area element is what I am saying. It is a ds. Here also This is ds. This is also small area element. It is also ds. Here also small area element ds. Right. So what is the direction of this one? Yes, I will show that. The direction of this area vector will be like this. This is ds bar direction. But the direction of electric field strength at any point on the surface will be in the same direction because of the symmetry of charge distribution. So, and also the magnitude of field strength at every point on the surface is constant. Here also the direction of O in this area vector, that will be in this direction. Okay, but the direction of electric field strength at that point will be in this direction. This is E bar. Again, if you consider this small area element, here the area vector direction is for like this. Okay, but the direction of electric field strength at that point also in the same direction. So I will show here also. So this is the direction of ds bar, right? The direction of field strength at this area element also ds bar. Similarly, you take any point on the spherical surface that will be perpendicular to that spherical surface at that point. E bar direction at every point on the spherical surface will be like this, right? So since the ds bar and E bar are both are in the same direction, the flux through the small area element here at anywhere, that is equals to the flux through small area element equal to E bar dot ds bar. Then the total flux through this entire surface equal to, we should integrate E bar dot ds bar. So the total flux phi is equal to surface integral of E bar dot ds bar, that equal to E ds cos 0, that equal to integral of E ds. Okay. Now let us go for the next slide. Yes. So now I am writing this surface integral E bar dot ds bar equal surface integral E ds. Since E is constant at every point on the sphere surface because of the symmetry of charge distribution, since all points on the spherical surface are at the same distance, here field strength magnitude is constant. So right outside of the integral, E into surface integral of ds. But the closed integral of ds is the total surface area of the sphere, that is 4 pi r square. So therefore, closed integral E bar dot ds bar equal to 4 pi r square. Okay. So what I am saying, the total flux through the entire surface is equal E into 4 pi r square. But what we have the Gauss law? According to the Gauss law, the surface integral of E bar dot ds bar equal 1 by epsilon naught times to the charge enclosed by that surface. Charge enclosed within the surface. So that is already, we consider the charge distributed over the sphere, how much? Q. Okay. So in the Gaussian surface, charge enclosed here equal to Q. So therefore, now E into 4 pi r square equal to Q by epsilon naught. From this, E equal to 1 by 4 pi epsilon naught Q by r square. So therefore, this is the electric field strength outside of the sphere. You observe this expression here, E inversely proportional to r square. Okay, we consider a point, external point from the center O at the distance r, that the field strength we got the expression 1 by 4 pi epsilon naught Q by r square. If sigma is the surface charge density, then sigma is equal to total charge by total area. So total charge distributed over the conducting sphere, how much? Q by total area of the sphere 4 pi r square. Then you will get Q is equal to, so this one 4 pi r square sigma. Substitute this value here, substitute this value in this equation, then 1 by 4 pi epsilon naught. So Q is 4 pi capital R square sigma by small r square. Then you will get E bar is equals to, so this one sigma by epsilon naught capital R square by small r cube into R bar, or sigma by epsilon naught capital R square by small r square into R cap you can write. If you write R bar here, we are taking R cube. If you write R cap here, that is the unit vector along the direction of R bar, then you have to write R square here. So this is the vector form. E bar equals sigma by epsilon naught capital R square by small r cube R bar. You can write it as E bar equals sigma by epsilon naught capital R square by small r square into R cap. Right. So this is the electric field strength at the external point of the conducting sphere. Now, so let us take on the surface. Next, go for next slide. Yes. The point P lies on the surface of the conducting sphere. Okay. Then simply we substitute small r equal to capital R. Okay. Small r equal to capital R. Then the formula would be what we get, E is equal to 1 by 4 pi epsilon naught Q by capital R square. Right. But Q by 4 pi, the charge by 4 pi R square is the charge density sigma. So that substituting that, then you will get, then E is equals to sigma by epsilon naught. In vector form, we can write, E bar is equal to sigma by epsilon naught into n cap, where n cap is the outward normal unit vector at any point on the surface. Okay, E bar equals sigma by epsilon naught n cap. So this is the maximum value. The field strength is maximum on the surface. E maximum equal 1 by 4 pi epsilon naught Q by R square. Okay, sir. Now, let us go for another third concept. So what is that? Yes. If we consider a point P inside the point, so here we have seen the three cases. The first, external point. The second one, on the surface. The third one, internal point. If we consider the point P inside the conducting sphere, then what is the concept? Right, sir. So I will explain here. So this is a uniformly charged conducting sphere, what we consider, right? The radius of the sphere is capital R. Now I consider a point P at the distance small r from the center. Now, so here if you consider the small area element, ds bar, so the direction of this ds bar will be perpendicular to the surface, right? But similarly, the direction of electric field strength is always, due to the symmetry, normally outwards. Here E bar, ds bar both are in the same direction. Then the flux through the small area element equal to E bar dot ds bar. The flux through the small area element is E bar dot ds bar. Okay. But we have to calculate the total flux. The total flux through this entire surface. The flux through the entire this inner spherical surface, that is we have to show the surface integral of E bar dot ds bar equal to surface integral EDS cos 0, because here E bar ds bar in the same direction, theta 0, cos 0 1, surface integral EDS, right? Since the field strength is constant in magnitude at every point on this spherical surface, right, E outside, the surface integral of ds is equal to what? The surface integral of this ds, that is the spherical surface area of this one, that equal to 4 pi r square. So we got E into 4 pi r square. But according to Gauss' law statement, what we have, the surface integral of E bar dot ds bar equal to 1 by epsilon naught times to the net charge enclosed by this closed surface. But there is no charge inside of this surface. Why? Because in the case of conducting sphere, okay, in the case of charged conducting sphere, Here charge resides on its surface only. Charge resides on its surface only. Okay. Charge distributes on its surface only. There is no charge inside of the conducting sphere. So here Q net equals to 0. This is not EMF. Q net charge Q equals to 0. So what I am saying, this value equals to 0. Then surface integral E bar dot ds bar equal to 0. Therefore, E is equals to electric field strength E equal to 0. The conclusion is electric field strength at any point inside of the conducting sphere must be equals to 0. Right? Equal to 0. The reason is there is no charge inside the sphere. Okay. So the important point is when the charge in conducting sphere, in the case of charge conducting sphere, since the charge is distributed only on the surface and there is no charge inside the conducting sphere, electric field strength at every point inside of the sphere is 0. Hence, the field strength at the center also equals to 0. Right, sir? Now, so if you see the graph, so the graphical representation is will be like this. Okay. Here the graph is drawn. The graph is drawn between the distance versus electric field strength, right? So you consider, right? I will draw the, just observe here. Yes. So this is the conducting sphere, right? Okay. So at the center, no field strength, right? From center to at any point inside of the sphere, center to the surface, how much field is 0. Therefore, there is no points graphically. On the surface, field strength is maximum. So this value is equals to what? So I will show this. So at R is equals to, right? Now the graph will be like this. So this is at R equal to capital R, that is on the surface. But on the surface, the field strength will be 1 by 4 pi epsilon naught Q by R square. So this is maximum. As we move from surface to the external point, here E inversely proportional to R square. So that is E inversely proportional to R square. Right, sir? Okay. So what I am saying, inside of the conducting sphere at every point field strength is 0. On the surface field strength is maximum. That value equal 1 by 4 pi epsilon naught Q by capital R square. And for external point, E value decreases according to E inversely proportional to R square. It is inversely proportional to the square of the distance. Hence we are getting the curve here. Right. So this is the graphical representation of a variation of field strength with the distance. Now, the second case. The second case is volume charge distribution in the case of uniformly charged non-conducting sphere. So here you consider a non-conducting sphere which is uniformly charged with the charge density rho equal to charge per unit volume. Then we write since the charge Q is distributed throughout this sphere, then rho would be the total charge Q by the volume of the sphere 4 by 3 pi RQ. Okay, because the radius is capital R, the volume of this non-conducting sphere is 4 by 3 pi RQ. Then volume charge density is given by rho equal to Q by 4 by 3 pi RQ. Here our intention is we have to calculate the field strength at external point P1, on the surface P2, and internal point P3. Okay. So first you consider the point P1, which is at the distance R from the center. the point P2 on the surface, which is at the distance capital R, that is the radius of the sphere, and the point P3 is at the distance small r1 from the center. Okay, so to calculate the field strength, at the point P1, you have to imagine a Gaussian surface, a Gaussian spherical surface which is passing through the point P1. Here the point P1 lies on the Gaussian surface. Right. Now, so I will draw that. On the spherical surface, this is a small area element, sir. You consider at any, on the spherical surface, you consider a small area element at any point, sir. So this is a ds, it is a ds, it is a ds. So what is the direction of this area element? That will be perpendicular to this area, ds bar direction. So that is, so what I am saying here, ds direction is this one, right? But due to the symmetry of charge distribution, electric field strength at every point on the spherical surface is normally outwards. Okay, normally outwards. So that is, I am showing on this point, at this point P1, the direction of, at this point P1, the direction of electric field strength is in this direction. This is E bar direction. Okay, or you can, let us change the color. The direction of electric field strength is in this direction. This is E bar. I am showing this. The direction, this one, it is capital E bar direction. Okay. E bar direction is denoted with yellow color. DS bar direction is denoted with orange color. DS bar direction, E bar direction, both are in the same direction. So if you want to show the same here I will show here the direction of DS bar is okay. The direction of DS bar is this one. This is the E bar direction. Okay, E bar direction, and the direction of small area element. This is DS bar. Right. I am writing. This is capital E bar direction. Okay, and yellow color, that is DS bar direction. Right, sir. Here also E bar and DS bar. You take any point. If you take any point on the surface, so the direction of field strength is normally outwards. It is radially outwards, like this. E bar direction will be like this. Okay. Right. So first you consider small area element, this one, sir. So here DS bar and E bar both are in the same direction, and the flux through this small area element, we write it as what? That is E bar dot DS bar. So flux through this small area element d phi equal to E bar dot ds bar. But the total flux through this entire spherical surface, entire Gaussian surface is equal, we have to integrate the d phi. So integral of d phi equal to integral of E bar dot ds bar. Right? So now let us extend our concept, right? Here. So this, all these things explained, right? So if you consider the point P, so this is the external point. Here d phi is equal to E ds cos 0, that equal to E into ds. Right, sir? Now the total flux through this entire surface, phi is equal to, that is integral of d phi equal surface integral E ds. Since E is constant at every point on the sphere, as we discussed in the case of conducting sphere, here also field strength at every point on the surface, magnitude constant. So E written outside, surface integral of ds. But integral of ds, the surface integral of ds is the surface area of this sphere, that is 4 pi r square. Okay. So then applying the Gauss law, according to the Gauss law, we have this E bar dot ds bar should be equal to Q by epsilon naught. Okay. E bar dot ds bar should be equal to Q by epsilon naught. Then substituting this value here, substituting that value here, this value substitute here, we get E into 4 pi r square equal Q by epsilon. From that, E outside equal 1 by 4 pi epsilon naught Q by r square. Okay. So this is the expression E equal to 1 by 4 pi epsilon naught Q by r square. This is the required expression. You observe the expression, it is very clear that, right, E inversely proportional to r square. So in the case of external point, the field strength is decreasing with the distance. According to the relation, it is inversely proportional to square of the distance, right? So if you consider the point P2, which is at the distance capital R, therefore simply you substitute small r equal to capital R there, then you will get E on surface equal to 1 by 4 pi epsilon naught Q by capital R square. Okay, so that is, you can understand here. Yes, E into 4 pi r square equal to Q by epsilon naught. E surface is equal to 4 pi 1 by 4 pi epsilon naught Q by r square. So this is the electric field strength on the surface of the non-conducting sphere, sir. Right. Now, if you consider the point P inside of the non-conducting sphere, so how to calculate the field strength, right, sir? Now, here the point P3 is inside of the conducting sphere, which is at the distance R1, sir. Here also you consider a small area element ds, right? Small area element ds. Okay, I'm showing this. This is small area element ds. Now the direction of ds bar will be like this. Similarly, the electric field strength is always normally outwards. E bar direction is like this. So E bar ds bar are in the same direction. Hence the flux through the small area element is E bar dot ds bar. That is a d phi. Then the flux through this total entire surface, inner spherical surface. This is the Gaussian surface. The flux through this total entire surface equal surface integral of E bar dot ds bar. Then we get this one, that is phi 3 equals to E into surface integral ds equal q1 by epsilon naught. Don't confuse. Here E bar ds bar in the same direction. Angle between E bar ds bar is 0 degree. E bar dot ds bar equal E ds cos 0. That is E ds. D phi equal to E into ds. Then the flux through this flux through the total entire surface is surface integral of E ds. Since E constant, it is written outside. Integral of ds equal to, according to the Gauss law, 1 by epsilon naught times the charge enclosed by this small area. Okay, the charge enclosed by this small sphere, that is q1. The total non-conducting sphere, the total conducting non-conducting sphere have the charge, total charge q. But inner sphere, this portion of the sphere has only the q1 charge. Hence, have written 1 by epsilon naught into q1. Okay. Now, integral of ds is equal to what? That is 4 pi r square, right? Integral of ds is equal 4 pi r1 square. Then we get this one, e into 4 pi r1 square equal to, that is q1. q1 equal to this substituted. What is that? q1 equal to we have rho into 4 by 3 pi r1 cube. Because rho is the volume charge density, rho equal to charge by volume, then the charge within this sphere q1 equal to rho into the volume of this sphere 4 by 3 pi r1 cube. So this value substituted here, sir. So this value substituted here. Okay, q1. Then we are getting E into 4 pi r1 square equal to rho 4 by 3 pi r1 cube divided by epsilon naught. Right. So both sides 4 pi cancel. R1 square cancel. Then we are getting what we get. Then E inside equal to this one. E inside equal to this is rho by 3 epsilon naught into R1. Here rho is constant, volume charge density. Epsilon naught is permittivity of free space, that is also constant. Here E depends on what? E depends on R1. Okay. So it is very clear electric field strength at the interior point of the non-conducting sphere is directly proportional to R1. Here, if you substitute R1 equal to 0, R1 equal to 0 represents what? That is the case of the point at the center. So when you consider the point at the center, in that case R1 equals to 0, then E inside equal to 0. So field strength at the center equal to 0, right? Field strength at the center equal to 0. As we move from center to the surface, right? Center to the surface, E increases linearly, E directly proportional to R1. Okay, so therefore field strength will be maximum at this point. On the surface of the non-conducting sphere at every point, field strength is maximum. That value equal to, already we discussed, 1 by 4 pi epsilon naught Q by capital R square, right? Similarly, if you move further, as we are moving from surface to outside of the point, here E decreases. So there we got the formula equal 1 by 4 pi epsilon naught Q by R square, small r square. So for outside point, E inversely proportional to R square. On the surface, E is maximum, that value is 1 by 4 pi epsilon naught small q by capital R square. At the center, E equal to 0, and as we are moving from center to the surface, field strength is increasing, and the relation is E directly proportional to R. So if you see the graphical analysis of this variation of electric field strength, in this case, so you can understand from this figure, sir. So here what we are doing, here the graph is drawn between the distance versus, right, the distance versus electric field strength, right? At the center field strength is 0, this one 0. Okay, as we are moving from center to the surface, field strength increases linearly up to the surface. So here E is maximum, so this one is maximum, it is maximum, that equal 1 by 4 pi epsilon naught Q by capital R square. As we are moving outside, okay, outside point from the surface, here E decreases like this, E inversely proportional to R square, right? So this is you have to understand from this graph, sir. Okay, now, so what are the conclusions of this lecture? The first, what is the Gauss law? Yes, the total electric flux emerging from any closed surface is equal to 1 by epsilon naught times to the net charge enclosed by that surface, right? So that is mathematically we are writing E bar dot ds bar equal to 1 by epsilon naught times to the charge enclosed within the surface. Okay. So after that, we discussed that now electric field strength due to a uniformly charged conducting sphere. So in the case of uniformly charged conducting sphere, we should remember that charge will be distributed only on the surface. Charge resides on the surface only. Charge will not distribute inside the sphere. So that for outside external point, the formula is this one. What is that formula? For external point, field strength is E equal 1 by 4 pi epsilon naught Q by R square. In terms of sigma, the formula is this one. In terms of sigma, E equal sigma by epsilon naught capital R square by small r cube into R bar. On the surface, the field strength formula is this one. 1 by 4 pi epsilon naught Q by capital R square. In terms of sigma, okay, in terms of sigma, E on the surface equal sigma by epsilon naught. Inside of the conducting sphere, then at every point inside of the sphere is 0. Therefore, obviously, the field strength at the center of the sphere also equal to 0. So that is we discussed regarding the uniformly charged conducting sphere, right? Now, after that we completed the discussion of field strength due to the non-conducting sphere. So there what we discussed here, sir. Here, in the case of non-conducting sphere, charge not only distributes on the surface, that can be distributed throughout the volume of this sphere, right? For external point, for external point, we are getting the field strength. This one, this is this is 1 by 4 pi epsilon naught q by r square. It is r square, sir. 1 by 4 pi epsilon naught q by r square. Not this one. It is 1 by 4 pi epsilon naught. Okay, q by r square. You have to correct this one. Q by r square. So on the surface, 1 by 4 pi epsilon naught on the surface, the formula we got this one. Q by capital R square. Simply we substituted small r equal to capital R. So for the point inside of the non-conducting sphere, then the expression we got is E inside equal to rho R1 by 3 epsilon naught. Since rho is constant, because uniformly charged non-conducting sphere we are saying. So at every point rho is constant. That is charge per unit volume at every point of this conducting sphere is constant throughout this volume. So then here E inverse E directly proportional to R1. Therefore, electric field strength increases linearly from as we are moving from center to the surface. Right. The variation of the field strength is shown here. Here the field strength taken on y-axis, the distance taken on x-axis. Right. So from center to the sphere surface, the field strength is increasing linearly. So on the surface or at the surface, field strength is constant at every point. That value is 1 by 4 pi epsilon naught q by r square. For external point, E again decreasing such that E inversely proportional to square of the distance square. So these are the things we discovered in this chapter, in this lecture. So from this, the expected questions are: derive an expression for electric field strength. Okay, electric field strength due to a uniformly charged conducting sphere. Or the second question, using Gauss's law, obtain an expression for electric field intensity due to a uniformly charged non-conducting sphere. So that this is also volume charge distribution. This question we will discuss in the next class, sir. Right? Okay. So these are the very important questions, right?